The next example is a kinematic source simulation, and Nico will be presenting that. So Nico, you can go ahead and share your screen. Nico's and please also introduce yourself.
Okay, so hi, I'm Nico Schliwa. I'm a PhD student of Alice, working currently from LMU in Munich. I'm interested in dynamic rupture simulations, for example, of the Ridgecrest earthquake. And I'm also doing this dynamic source inversion where we try to invert for frictional and stress parameters on the fault. And I will now walk you through the Northridge example. And at first I will show you just a few overview slides of the earthquake. Okay, so the second example will be a kinematic rupture model of the 1994 Northridge earthquake. So the Northridge earthquake had a magnitude of 6.7, and 60 people were killed, more than 7,000 injured, 20,000 people got homeless, and more than 40,000 buildings were damaged in Los Angeles and other countries. And there was a lot of additional damage. It was caused by secondary causes like fire, and the damage was estimated to be between $13 and $20 billion, which makes the most costly American earthquake since the Great San Francisco earthquake in 1906. So here you can see a map of California and like the faults and few large earthquakes. And here is the epicenter of the Northridge earthquake, and it was quite close to Los Angeles and had a depth of 18 kilometers. And what was special about this earthquake is that it's a blind thrusting earthquake, which means that the fault was completely below the Earth's surface, so there was not any surface expression, and also the fault was not mapped. So the people did not know that there was a fault, and so they did not know about the potential hazard. And it was actually located directly under the city of Northridge, which then experienced a very severe shaking. And so the model that I will show you now is a kinematic model, which means that we don't solve a dynamic rupture like a frictional failure problem on a prescribed fault, but we have description of slip rates. In this case, it's just a bunch of point sources, which are then connected and lead due to the superposition to a finite fault model. And these kinematic descriptions are usually inferred from solving an inverse problem using strong ground motions, teleseismic ground motions, or GPS satellite observations as input. But they have a problem. They are strongly non-unique and often physically implausible, and they do not give any description of the stresses and the frictional forces that are involved. Yes, I think you're already running the Docker notebook. So now you just have to click here on the Northridge folder and then on the Northridge notebook, and we can go through it together. Okay. So the first part is the mesh generation, again with Gmesh, or actually the Python API of Gmesh. And what will be special about this mesh now is that it uses the topography, and actually implementing or integrating topography into a Gmesh mesh is not that easy. So I will not go too much into detail here, but if you're interested, then you can just like go through the code again and see how it exactly works. So at first, you have to download topography data. You can do this, for example, from NASA, and then you start with reading in the data, sampling it to your domain space, and also like sampling it to the density that you need for your mesh. Then there's an important step. So usually you get the topography in latitude, longitude coordinates, but SeisSol uses Cartesian coordinates. So you have to do a projection. Sorry, just. Yeah, and here you can see now the model domain with the epicenter of the Northridge earthquake, and left plot in longitude, latitude coordinates, and the right one in UTM Cartesian coordinates. Okay, then now we are generating the mesh. There are a few important parameters here. You specify your desired domain size. Then here you specify the target element size for like overall elements and for elements at the surface. Maybe later you can play a bit around with this parameters, like reducing this element size, and then try how much longer the simulation will run. Yes. Yeah, and then so this is then the part where you add the topography to your model. Then you have to add the volume to your model, and then in the end you just connect everything together. And then there's one last important step where you have to assign physical boundaries to the different boundaries of your domain. Like you have the free surface domain, which needs another tag than your other domains, which are absorbing boundaries. And this is important for SeisSol to know which boundary conditions it has to use. And then we are generating the mesh. I don't know why, but I get a warning. I think other people don't get the warning. But anyway, the mesh generation was successful. And now we just have to convert the mesh into the right format for SeisSol, and then we are ready to go simulation. We also have to convert this standard WebGIF format of the kinematic source to a format that is suitable for SeisSol, which we're doing now this step. And now we can run SeisSol. Now you see it's starting the computation, and it should be much faster than the previous problem, because it's only a kinematic problem. So we don't solve this frictional failure on the fault. While the model is running, can maybe a few things more about the comment to start SeisSol. So Sebastian already told you that if you have more cores, then you can like increase the number of threads. So on your local machine, probably just increasing number of threads is the best way, because you use shared memory. But if you're, for example, on a supercomputer and you use different nodes which don't share memory with each other, then you need different MPI ranks for each node, and then you would increase this number for that you have like one MPI rank for each node. So this is like the parallelization step of a system that does not share the memory. Okay, it's quite fast. I think I can have a quick look at the parameter file. This model, which you can see at the look at this. Okay, no. Okay, at the moment we are running the model purely elastic, but in a second step we run the same model with another SeisSol executable, which uses a viscoelastic attenuation, and for this we need this additional parameters in the parameter file. And some other interesting things, parameter files. Here you have to enable the boundary conditions. For this kinematic problem, default boundary is disabled because we just have the superposition of point sources. And here you specify the mesh that you want to use. And here you can turn off and turn on and turn off the output. So here we did turn off the volume output, but we turn on the surface output, and we can also specify a refinement of the surface output. So if the refinement is 1, or no, if you have no refinement, then you would just get like a single value for each cell. But if you increase the refinement, then you will get like sub points for each cell. And this works because SeisSol uses a high order method. So you have a polynomial representation, a high order polynomial representation of your fields within each element. So you can also like output these sub-element points. And then you specify the end time, which is 10 seconds in this case. Now the simulation is already done. Took a bit less than 3 minutes. We'll actually already start the next simulation with the viscoelastic attenuation. And while this is running, I will also show you the material file for this example. The material file is quite simple. It needs 5 parameters, and the density, mu and lambda, so the Lamé parameters, and the Q value for P waves and the Q values for S waves for the viscoelastic attenuation. And we have a simple 1D structure. You specify certain values for certain depths, and then in between they are linearly interpolated. And now I will show you how you can visualize the surface output in ParaView. And for this, I already copied the output from Docker to my laptop. I can open this Northridge output. You always open the XCMF file. Always with this usual XCMF reader. Then important step, you have to click on apply. Yes. And then you have here the surface output. This is the partition, because you did only use a 1 MPI rank. This is just only 1. And then you can visualize wave field. So these are the different velocity components. So and here you can see how the wave field propagates across the surface. Now it's strongly saturated, so you have to rescale it. And in ParaView, you can also calculate other quantities from your input parameters. And you do this with this calculator here. You can, for example, calculate an absolute velocity. Then just square root of v1 squared plus v2 squared plus v3 squared. And now you have the absolute velocity of your wave field, but now the color map is not really suitable for this. So you can also change this to, for example, to this one. Also invert it. Now it looks better. And now you can see how the absolute wave field propagates across the surface. So you can also derive another quantity from your input with the calculator. When you go to point data, then you also have the coordinates. So you can just, I will call this topo, and it's just the Z coordinate. So now you can see your topography. You can use this color map, which fits better to topography. We just set this value a bit different because we don't really have an ocean in our topography. Now it really looks like, topography should look like. And now I want to superimpose like the wave field above the topography. And for that, I use a filter, which is called transform. And I just move our wave field a bit up, so it's above the topography, like this. But now we don't see the topography anymore. Therefore, I will use another feature, which is the threshold here. And I want that only values of the wave field that are above 0.1 meter per second are shown, and the other ones are hidden. And then, you have your wave field above the topography. Then, you can see how the wave field propagates across the topography. Okay, now we'll have a look to the second simulation, the viscoelastic one. And it's now also done. But it took nearly 6 minutes, so nearly twice the time, which shows that like integrating more physics in the models will lead to more computational costs. And I think that's actually already everything from my side. So are there any questions about this example?
There's some lively discussion going on Slack. It would be good if anyone has more questions to ask now directly. We are very good in time, and then I think it's very fast going through the going through the examples. Do you want to maybe see something again? Some ParaView with tricks, some ways how to visualize things, or I don't know, did everyone capture what Nico did to use some simple ParaView filters and things? Did you understand how the kinematic source is set up? I see people typing. Very well trained now using Slack. But you can also speak up. Okay, if that's not the case, we go to the last example. Thanks a lot, Nico. I asked Nico very short notice, so thanks a lot for chipping in. And